Hello and welcome to TJC Physics. This video continues a series of videos I've made about waves, or simple mechanical waves. In the previous video, I introduced the concept of a standing wave. I would like to sort of drill down on that a little bit and talk about a specific case of a standing wave on a string that is fixed at both ends. On the screen, you can see a simulation of a standing wave on a string shown in slow motion. The yellow part is the string, and you can imagine we've taken a slow motion video of it as it vibrates back and forth. Think of a guitar string being plucked, or two people holding a skipping rope moving it around. You can see at the very ends, those are fixed. Those are nodes. And by the way, this isn't my simulation. I found this on a website. I'll include a link to it below in the description of the video so that you can go and play around with it yourself. Now, standing waves only occur at specific frequencies. And when you hit these specific frequencies, you get certain patterns on the string. So this first pattern here shows two fixed ends and the middle of the string moving a lot. So those parts of the string that aren't moving, specifically the ends here, are called nodes. And where the string moves the most is called an antinode. So this particular pattern has one antinode and two nodes. And if the string is fixed at both ends, they will always be nodes. Now, standing waves only occur at certain frequencies. This pattern with one antinode occurs at what we call the fundamental frequency, which is the smallest frequency of wave that will cause a standing wave pattern to occur on a string fixed at both ends. In order for us to visually draw standing wave patterns, we tend to draw the envelope of the wave. And as you can see here on the screen, the envelope is the white lines that indicate the extreme edge of the medium's motion. So it kind of looks like a little sort of eye-shaped, but we sometimes draw that as a visual representation of the standing wave n equals 1 that occurs at the fundamental frequency. We also call this the first harmonic of the string. Now, if you increase the frequency past this fundamental frequency, you will destroy the pattern and you won't see anything. However, if you keep increasing the frequency, at some point you'll hit a frequency where you get this pattern. This pattern with two antinodes is called the second harmonic, or the first overtone. You can see in this pattern, which we can also call n equals 2, you have three nodes and two antinodes. So drawing it visually, we can take the extremes of the motion here and draw the envelope for it to represent the second harmonic and the first overtone. Here is the third harmonic, or n equals 3, also known as the second overtone. Now start to notice the patterns. We have three bumps here for n equals 3 and the third harmonic. Let's scroll back a little bit and notice that the pattern for n equals 2, or the second harmonic, had two bumps. And if we even scroll back to the beginning, you'll notice the pattern for the first harmonic had n equals 1, or one bump. So you can do a lot with pattern recognition. Fundamental, or n equals 1, is one bump. N equals 2, the second harmonic, is two bumps. And n equals 3, the third harmonic, is three bumps. So imagine the fourth harmonic. There should be four bumps. And there it is. Now I'm also going to put a link to a YouTube video down below in the description that shows somebody actually performing this experiment on an actual string attached at both ends. It's pretty cool and I recommend you watch it. In an upcoming video, we'll talk more about the mathematics behind these patterns and see how we can solve problems with them. Well, thank you for watching and have a great day.